In classical physics, light can be thought of as a wave of electric and magnetic fields. Suppose that we have two of these electromagnetic waves in the exact same region of space. At each point in space and time, their electric fields will add like vectors, and their magnetic fields will add like vectors. In this case, the two waves add together to form a new electromagnetic wave with a higher amplitude. Now let us consider a new scenario. We again have two electromagnetic waves in the same region of space, but this time they are not oriented in the same direction. As before, the electric field will add like vectors. And the magnetic fields will add like vectors. This time, the two waves add together to form a new electromagnetic wave with its orientation changed as shown. Now let us consider yet another scenario. This scenario is the same as the previous one. Except that in this case, one of the two original electromagnetic waves is ahead of the other one. As before, the electric fields will add like vectors. And the magnetic fields will add like vectors. This time, the new electromagnetic wave continuously rotates through space and time as shown. Now let's consider a slightly different scenario. This time, it is the other one of the two original electromagnetic waves which is ahead. In this case, they will add together to form a new electromagnetic wave that continuously rotates in the opposite direction of the previous scenario. If light consists of waves that are all continuously rotating in the same direction, we refer to it as circularly polarized light. On the other hand, if the light consists of electromagnetic waves that are all aligned in the same direction as shown, we refer to it as linearly polarized light. Most light sources, such as light bulbs, candles, and the sun, produce light that is composed of electromagnetic waves that are all oriented in different directions. We refer to this as unpolarized light. Each electromagnetic wave is composed of both an electric field and a magnetic field that are 90 degrees to one another. In order to help visualize the upcoming explanations, let us just show the electric field, though the magnetic field is still always present. Every electromagnetic wave can be thought of as the combination of two other electromagnetic waves, which are oriented in one of these two directions. There are some materials that block electromagnetic waves oriented in one of these directions, but allow electromagnetic waves that are oriented in the other direction to pass through. Therefore, regardless if it is circularly polarized, linearly polarized, or unpolarized light that enters the material. Only linearly polarized light is able to exit the material. If the incoming light is already linearly polarized, and it is oriented in the direction in which the material blocks electromagnetic waves, then all the light will be blocked completely. On the other hand, if we rotate the material, then the direction in which the electromagnetic waves are blocked will also rotate, and the light will now pass through. Suppose we start out with unpolarized light. After it passes through the material, we will have linearly polarized light. We therefore refer to this material as a linear polarizer. Suppose we add another linear polarizer, as shown. Now suppose we rotate the second linear polarizer. If the two polarizers are 90 degrees to each other, no light is able to pass through. Now let us add a third linear polarizer, located in between the first two, as is shown. Suppose we rotate this third linear polarizer by some amount between 0 and 90 degrees. Its axis for blocking light and for allowing light to pass through will rotate as shown. The linearly polarized light entering this polarizer can be thought of as a combination of two electromagnetic waves, each aligned along one of the polarizer's two axes. Only one of these two electromagnetic waves will pass through. Therefore, the net result is that the total electromagnetic wave has been rotated from its previous orientation. The new electromagnetic wave leaving this polarizer can also be thought of as the combination of two other electromagnetic waves, oriented as is shown. One of these two waves has the ability to pass through the next linear polarizer. When we started out with just two linear polarizers rotated 90 degrees to each other, no light was able to pass through. But when a third linear polarizer was added in between them, now light is able to pass through our three polarizers. The amount of light that is able to pass through depends on the angle of this third linear polarizer in between the first two. In empty space, light always travels at the same speed from the perspective of all observers. But light can slow down when it passes through a material. In the case of some materials, light will slow down by a different amount depending on which direction the electromagnetic wave is oriented. Suppose that the difference by which the waves are slowed down is 1/4 of a wavelength. In this case, we refer to the material as a quarter wave plate. When linearly polarized light passes through a quarter wave plate at a 45-degree angle to the wave plate's two axes, the wave can be thought of as being composed of two different electromagnetic waves, one of which is slowed down by a quarter wavelength more than the other. The waves leaving the quarter wave plate add together as vectors. When linearly polarized light passes through a quarter wave plate, it is converted into circularly polarized light. If the circularly polarized light passes through another quarter wave plate, the incoming circularly polarized light can also be thought of as two waves, one of which is slowed down by a quarter wavelength more than the other. Therefore, when circularly polarized light passes through a quarter wave plate, it is converted back into linearly polarized light. Quarter wave plates convert linearly polarized light into circularly polarized light, and they convert circularly polarized light back into linearly polarized light. The phenomena described here plays a very important role in much of our technology. And it plays a very important role in experiments in quantum mechanics which challenge our assumptions about the nature of reality.